For decades, computing speed relied on a strict serial architecture. A processor takes an instruction, applies it to a piece of data, and moves to the next. Tasks are executed sequentially, one after another, forming a rigid bottleneck governed entirely by the clock speed of a single CPU. The engineering solution to this limitation is parallel processing. Instead of pushing one processor to run faster, you reduce execution time by splitting a massive workload across multiple processing elements simultaneously. But dividing a workload requires a structural choice. Are you dividing the data, or are you dividing the instructions themselves? If you divide the data, you build a SIMD architecture, single instruction, multiple data. In a SIMD processor array, a single control unit broadcasts one operation, like addition, and applies it to a massive array of different data elements all at the exact same time. Conversely, if you divide the tasks, you build a MIMD architecture, multiple instruction, multiple data. Here, independent processors handle distinct, complex instruction streams, executing completely different logical operations on completely different datasets simultaneously. Historically, achieving these parallel configurations required custom-built VLSI vector processors, resulting in massive, specialized mainframes before the industry shifted to clustering commodity CPUs. Yet, simply adding hundreds of processors to a circuit board does not guarantee a linear increase in speed. The true ceiling of computational power is dictated by the physical network connecting them. In any multiprocessor system, distinct CPUs cannot work in total isolation. They must constantly communicate to share data values and coordinate task completion. Executing an instruction locally inside a CPU takes a fraction of a nanosecond. Routing a piece of data between hundreds of distinct processors without incurring massive delays is an exponentially harder physics problem. This physical routing grid is called the interconnection network. These are the physical tracks that dictate the overall speed of the entire system. If this network is poorly designed, processors spend more time waiting than calculating. System lag is driven by specific variables: physical routing limits, decentralized arbitration overhead, and the constant threat of message collisions. As parallel architectures scale from tens to thousands of nodes, the primary engineering challenge shifts away from how fast a chip can process data to how efficiently the network can move it. The simplest way to build an MIMD system is through Uniform Memory Access, or UMA. In an UMA architecture, all processors share the exact same primary memory pool. They connect to it through a single shared communication medium, typically a data bus. This geometry guarantees that the time it takes to retrieve a piece of data is strictly uniform for every CPU on the board. But the shared medium creates a severe arbitration problem. Because there is only one path, processors must constantly listen to every message to determine when the line is clear. When two processors attempt to transmit data at the exact same millisecond, the signals physically collide. Every single collision requires both processors to stop, wait a randomized interval, and resend the messages. This creates a compounding cycle of latency. UMA hits a hard scaling limit very early. Adding more processors to a shared bus actually decreases the system's overall performance because the exponential rise in collision rates chokes the entire network. To bypass the bus bottleneck, system architects implement switched media networks. Instead of sharing one line, each processor is given its own dedicated path to a switch node. This physical separation allows multiple messages to travel simultaneously without colliding. To evaluate these switched networks, we look at two mathematical metrics. The first is diameter. Diameter is the maximum distance, counted in edges, that a message must travel to get from one end of the network to the other. The second metric is bisection width. This is the absolute minimum number of edges that must be severed to physically divide the entire network into two equal halves. A standard binary tree boasts a remarkably low diameter, scaling logarithmically. This low diameter guarantees travel times between any two nodes remain incredibly short. But the binary tree possesses a fatal structural flaw. Its bisection width is exactly 1. If nodes on the left half need to talk to nodes on the right, 50% of the cross-traffic must funnel through one single, solitary edge at the top. Optimizing for rapid travel time is useless if the system chokes on the volume of data. A successful topology must maximize bisection width. To survive high traffic, architects engineered higher-order networks designed specifically to widen that bisection bottleneck. The butterfly network solves the root bottleneck by drastically increasing its cross-routing, pushing its bisection width to n divided by 2. It achieves this high throughput by relying on a strict left-cycle shuffle and exchange link routing protocol to distribute the traffic load evenly. An even more robust topology is the hypercube. It also boasts a massive bisection width of n over 2, but it achieves this by operating on dimensional geometry. In a hypercube, nodes are addressed in binary. Two nodes are physically connected by an edge only if their binary addresses differ in exactly 1 bit position. The hypercube has a fatal manufacturing flaw. Because edge connections scale logarithmically, physical wire lengths cannot remain constant. You cannot print them uniformly on silicon. Contrast this with the 2D mesh network. Its bisection width is lower, but crucially, the physical length of every edge remains perfectly constant, no matter how large the grid gets. System architects abandon the mathematical perfection of the hypercube in favor of 2D meshes. The physical constraints of printing VLSI silicon demand constant edge lengths. To scale to thousands of processors, the architecture must abandon the central bus entirely and adopt non-uniform memory access, or NUMA. In a NUMA architecture, primary memory is physically distributed across the processors. This removes the single shared bus and massively increases aggregate memory bandwidth. But distributing the memory introduces a severe logical threat: the cache coherence problem. When a processor reads a piece of data, it copies it into its local private cache. If processor A takes that copied block and overwrites it with new math, processor B is left holding stale data. Its local copy is suddenly incorrect, and the system is out of sync. In a centralized system, processors simply snoop the shared bus to see if data has changed. Without a shared UMA bus, snooping is physically impossible. Hardware engineers solved this by implementing strict directory-based protocols. A centralized directory maintains an entry for every single cache block. It tracks the status, flagging it as shared if read-only, or switching to exclusive the millisecond a processor writes over it. Scaling forces a rigid trade-off. You abandon the simplicity of a shared bus, assuming the intense overhead of tracking data across a complex, decentralized board. This progression leads directly to the ultimate realization of parallel computing, the massive, distributed multicomputer. In these towering server clusters, nodes lack any shared primary memory whatsoever. The same memory address on two different processors refers to two totally isolated, distinct physical locations. Without shared memory, isolated processors interact strictly through message passing. They package requests and fire them across the network to coordinate actions. While entirely separating the memory perfectly solves the physical hardware scaling problem, it pushes the complexity onto the programmer, drastically increasing the difficulty of developing and debugging parallel software. The software must proactively manage load balancing. The program itself must guarantee that the work is divided evenly, ensuring half the processors don't sit idle while the other half are overwhelmed with data. High-performance computing requires far more than hoarding CPUs. True computational speed is achieved only when software is aggressively optimized to respect the physical latency, bandwidth constraints, and topological geometry of the machine executing the code.